So let's imagine that we have an initial speed of 20 meters per second. So that means this leg of the displacement triangle will be a 20t. Gravity's still doing its thing, as always. But let's say that we'll still use 10 for g, so half of g is 5, t squared. Let's say that my projectile keeps landing above ground, so I have a positive change in speed, so my delta h was 2 in this case, positive 2. And then that would result in some sort of range, and let's pick an initial angle, an angle of 30 degrees. So here's some projectile starting at 20 meters per second, flying for some amount of time, landing 2 meters or 2 whatevers. If we're going to have meters per second for speed, then this needs to be 2 meters displacement, or some number of meters. And so we can go around the block again. So we've been doing this sort of thing, but I ask you to extend your thinking a little bit more in this week's assignment. So you'll use some of these. You have 2 problems that will be like the last 2 problems of last week's homework, except I'm going to ask you to compare what the actual value of gravity would result into the rounding of it to 10. So just a little compare contrast there. So just a computational maneuver. Instead of putting 5t squared, it'll be 4.9t squared, etc., like that in your equations. And then I'm going to ask you to use some other equations of motion and take the analysis a little bit deeper. So that's what I want to give some time to right now. But first, we can address the time of flight. Well, if I want to know the time of flight, I'm going to have to pick a relationship that will give me the time of flight from this. And so the sine relationship will give me that. So if I sine of 30 degrees would be the opposite, 5t squared plus 2 over 20t. So that means I'm going to have a 5t squared minus 20 sine 30 times t, this is building a quadratic, plus 2 would equal 0. So that just comes from flattening that out. And I want you to take note of the fact this thing right here, this is our initial y speed. Initial speed, sine of theta. But this is where I would expect that we would use our computers and calculators to handle this for us, and we end up getting 1.8 seconds for time of flight. This is, consistent with what the problem we just did. It's all in that ballpark of 1.8 or 9 seconds, so this is unsurprising. So just a little bit of review. So we could, now that we know the time of flight, the cosine function, 30 degrees, would be range over 20 times 1.8. And so we'll get a nice 30.7 meters out of that when we compute that. Easy peasy. And the tangent relationship would give you the same number. I'll leave that for y'all to do if you are so inclined to do that. So that's just basic review of what we were just doing. Now we'd want to ask a more complicated question. So we could ask a question, where is this thing going to be at time equals 1 second? And so we're going to do this in regular Cartesian lingo. So you may not recall, but we had this equation that came out of our musings in a previous lecture, where the final y position is going to be the initial y position plus some sort of change. And one of the ways that that worked out when we did all the trigonometry was it worked out this way. Now that's a multivariable equation at the moment. It has x and y in it, and it also has time in it. So I could substitute the time value that I'm curious about of 1. That's why I picked it. That's a nice number to play with in this one. I don't think I'm quite as nice in the homework. I think it's like 2 or something like that, all right? And we could get rid of one variable, but then I have x and y. All right, so how do we get around this? Well, one way to do that is I can, in fact, rethink what x is here. In fact, x equals r, technically speaking. The x position is going to be the range, all right, which is going to be v naught cosine theta, that's the x part, times t. All right, so literally the speed times the time is going to give me that position. So I can rewrite this as y equals y naught plus v naught cosine theta, and I'm going to put the tangent theta in there. And our t minus half gt squared. And this cosine times tangent works out nice. So by the way, since we're starting at ground level, initial y is 0. So y would equal v naught, and instead of cosine times tangent, since tangent's sine over cosine, this is just going to reduce to sine. T is 1, all right? But I'll put it in there anyways, minus 5t squared. Now here's where, since with this, yes?
Would it be sine squared of t? So sine or cosine? No.
No.
No, it wouldn't.
The cosine's drop.
Yeah. Sorry.
No problem. So now, really what I have here is I have a function, y is a function of t. That's what I have. Just because I didn't start off writing it y as a function of t, doesn't mean it wasn't. In fact, initially it was y was a function of x and theta and t. Or theta and t, rather. Of course, theta is constant, so it wouldn't be a function of that. It would be an x and t. But I reduced a variable. And so if I want to know the y at 1 second, then I'm going to have 20 sine 30 minus 5. And that's just going to equal 5 meters. Because sine 30 is half, half of 20 is 10, 10 minus 5 is 5. So 1 second after launch, this ball will be, or projectile will be 5 meters off the ground. And we know from the other part of the problem that 0.8 seconds later, it's going to be 2 meters off the ground. So either, I don't know what its peak height is, we didn't address that, but we could use some other equation for that. And then, so that I know its y position, so now I should probably try to get its x position, all right? And that comes straight from the part that we substitute out, this right here. we have our equation for the x position. So we could literally, x will be 20 cosine 30 times 1. I mean, we could put that in there. And that gives us 17.3 meters. So where is the object at 1 second? It would be at a position of 17.3 and 5 in some number of meters. So in the Cartesian plane, that's where it's located. So we got the time from our regular analysis. We have the range at a particular time, so the x-coordinate is the range at that time. So just kind of understanding what we're writing here. And our vertical height at that time by using this position equation for the y direction, which had in it embedded the x position as well. There's another version of this part of the formula that involves cosine squared and speed squared and g. Those are other options we have, but we're not going to use it for this one. So now I ask the final velocity equation, and when I say velocity, velocity is a vector. Speed is the magnitude of velocity. So if I ask for speed, we wouldn't need to know the direction. But since I've asked for final velocity, we need to know its speed at impact as well as the direction at impact. So just the lingo of when I say velocity, you know that means a vector answer, and vectors have magnitude and direction. So we've got to figure that out. So this one takes us sort of out of using the displacement triangle, and we need to use the zeroth laws, and which basically come in the standard equations of motion. So one of those equations, switch colors here, final y velocity would equal the initial y velocity minus gt. Now, the way we wrote the zeroth law, the second zeroth law, we had second zeroth law would have been v equals v naught plus a delta t. That would have been the second zeroth law. That's the general version of velocity. Of course, g is downward directed, okay? So what we have here is a equals the minus g. So if a was a minus g, then I have minus gt for that. Also, we have the y directions. Up here, we didn't have any directions. We just had the general statement in the original part. All right, so be mindful of that. Let's clear that out of the way. So that means I can do some range in here. So I want to know that final y speed. Well, initial y speed is 20 sine 30. If I use the value of 10 for g just to keep things simple, we had 1.77, so it was 1.8 in the last one, but just to give you a little bit of precision there. So just remember, this is my v naught sine theta. That's what this is right here. Okay. And so this works out real nice. We'll get a nice clean number there. This will be negative 7.8 0.75 meters per second. So it won't reach its full speed that it started off in the y direction because it doesn't land at ground level. But it'll have a negative because it's going down at the end of that arc. It's heading down. So it makes sense that the y speed has a negative component. If I got a positive answer here, you would expect that, oh, something went wrong in my calculation, right? So that's part of the puzzle. What about the x speed? Well, we've already seen this already. Vx would be the initial speed times the x component of that speed. And so that's going to be 20 cosine 30. So the x component of speed, which won't change, all right, this is going to be 17.3 meters per second, which we had 17.3 meters for the range at 1 second, so that makes sense. All right. So now I have the two components, the y component and the x component of speed, and one of the things we're going to start doing is writing vectors in a particular way. So the initial speed vector could be written as, in rectangular form, as 17.3 comma minus 7.75 meters per second. That would be a standard way to write a rectangular vector in 2 dimensions. We just did that basic thing in Python, didn't we? Except we didn't have we used parentheses instead of those brackets. Same exact thinking. All right? So yes, I have an evil plan, coordinating all these things in the same place. So that would actually be an answer for the final velocity in terms of its magnitude. In fact, if I took the square root of the sum of the squares of those two parts, I would get back the 20 meters per second. All right? But now I need to know the direction of this vector. I'm hoping that y'all remember that if you want to know an angle, you have these inverse functions. And it's always, for tangent, it's going to be y over x. This is in your textbook, so you're responsible for this knowledge. Right? Ignorance of the law is no excuse. So now I can just plug in Chugsville. I have the two numbers. I have a negative 7.75 over a 17.3. So that means my angle, in this case, will be a negative 24.1 degrees. And so that makes sense. You would expect that it would, landing 2 meters off the ground or just at some zero height there, that the vector here would not have the same angle that it has here. In fact, its magnitude would have to be less. Had it fallen below ground level, we would expect that angle to be steeper because it would have longer to fall. All right? So now we have these two things together. This and this give me the direction. Now technically, rectangular version of velocity does give me direction because it has the x and the y direct parts. It's because if I were to plot that on an xy plane, I would get this right here. I would get a vector going from 0 down to negative 7.8 on the y and 17.3 on the x. I would get that arrow vector if I were to plot it on an xy plane. All right? This angle here, so I need to retract what I said a minute ago. I won't get 20 for this. I'll get something less than 20. And so the magnitude of that vector at this angle, I could write it in polar form. So V naught, back to the pencil here, would equal 19 meters per second, and I could put at an angle of negative 24.1 degrees. This right here would be a polar vector. And you had a trig or pre-calc course where you would have dealt with that briefly. It's a magnitude and an angle. So polar vector is a really handy way to give magnitude and direction and have a vector. It very explicitly gives you magnitude and direction. This much speed at that angle. It's clearly size and direction. Whereas the rectangular version, what we have here, it's implied, the direction's implied because you're plotting it on an XY plane, and you would obtain a graphical version of that vector. So that's basically the gist of what you're being asked to do in the next assignment.